Welcome to IT Pro TV. I'm your host, Don.
Coming at you live from San Francisco, California.
You're watching IT Pro TV.
Hello, and thank you for watching IT Pro TV, helping you level up with IT learning everywhere you go. I am your host, Zach Members, for this episode of CompTIA Linux Plus. Understanding TCP IP is the title of this episode, and once again, Don Pizzetta, our expert, is here to show us the way. Don, good to see you.
Hey, glad to be here, Zach. And if you've been learning about Linux, one thing that you know about it is that it is a network operating system. It was designed to work in networked environments from the very beginning, not like some of the other operating systems out there like Mac OS and Windows, where networking was bolted on after the fact. Here we've had it since the beginning. So if we are firing up a Linux box, the odds are it's going to be connected to the network, and we need to have a good understanding of that. So in this episode, what we're going to do is we're going to learn a little bit about the TCP IP protocol stack, which is what powers practically every network communication these days. We'll learn a little bit about how it works and its IP addressing structure, and then we'll see how to view all that inside of our Linux distro. So just kind of a quick overview of networking. It'll be a really useful thing to have.
Well, Don, how are IP addresses assigned?
All right, so with IP, with any kind of TCP IP-based network, you need addresses, and that means you've got to have a number assigned. Think of it as like a phone number, right? If you want to call somebody on the phone, you've got to know their number. And how do they get their phone number? Well, when they buy a phone, they sign up for a contract, and they get assigned a phone number at that time.
True.
Well, your computers are assigned numbers as well. They just don't have 2-year lease contracts assigned to them and all that stuff. But they do get assigned an IP to be able to use, and the IP has to come from somewhere. So let me show you, for example, here on the CentOS box that I've been using most of the show. If I go into a terminal, I can run IP space ADDR, right? And that's going to show me the IP addresses that I currently have on my system. Now, the IP ADDR command is a newer command. And when I say new in the Linux world, we really mean like in the last 10 years. It's not cutting edge new. But for years and years and years, we used another command, which was ifconfig, which would show you the configuration of your interfaces. But that's been replaced by IP ADDR. And it will show me my network adapters and their associated IP addresses. Here's my main network adapter right here, this ENS33, and I can see right here that it has a IP address of 10.0.11.49. That's the address assigned to this laptop. Now, I didn't assign that. It learned it. It got it from the network. There was a server out there, a DHCP server, that was handing out addresses. So when my computer fired up, it asked the network and said, could somebody please give me an IP address? And a server responded. That's the DHCP process is... It's actually pretty straightforward. They have an acronym for it called DORA, where you do a discover, offer, request, and acknowledgement. So discover, my laptop fired up and did a discovery and said, hey, could somebody please give me an IP? And when that message went out, a DHCP server heard it and responded back with an offer and said, here, I'll offer you this IP. What do you think? And then my laptop received it and said, you know what, I like it. I'm going to go ahead and request to keep that IP. And then the DHCP server acknowledges and says, okay, I got you. I'm assigning that IP to you. It's now yours, right? So that 4 little step process: discover, offer, request, and acknowledge. Well, all of that happened without me even thinking about it. I just turned the computer on this morning, and it got that address, and it had it. But there is a lot that actually goes on behind the scenes with this stuff. Here it was automatic. We might choose to do it manually. And either way, whether it's manual or automatic, where do these numbers even come from in the first place, right? Well, IP addresses all come from a giant 32-bit address pool. 32-bit just means that in binary, it would be 32 ones and zeros written in a line to form an IP. The IP that I'm looking at here is written in a decimal format. It's what we're used to as humans. And so I see 10.0.11, which I guess we could render that in binary, but .49. 49 is not a binary type thing. That's not zeros or ones, right? This is a decimal number. But if we were to convert that to binary, it would end up being 32 bits. In fact, if you want to learn more about how those addresses are calculated, you should jump over to our Network Plus show, because we spend entire episodes in Network Plus going over exactly how to convert those over and how they're all aligned. But for the sake of this show, where we just need to understand the addresses, let's boil it down a little bit more simple. This /16 right here is telling me that I'm on a network that contains a certain amount of hosts. And in the old days of networking, there were 3 different types of networks. There were Class A, Class B, and Class C networks. And they all used a subnet mask that would denote what part of the address was the network and what part of the address was the IP. So, for example, on my laptop, I am 10.0.11.49, right? Or you might see something at home, 192.168.0.1, right? That's the default IP of most home routers, or maybe 1.1, or something completely off the wall, like 85.122.71.9, right? Those are all valid IP addresses that I've written on the screen. And part of that address represents the network, and part of it represents the host. It's kind of like the street address on your house, or this building. So this building is at 7525 Northwest 4th Boulevard. Wait, Boulevard? Street? What are we? But it's Boulevard, yeah.
It's Boulevard, yeah.
I don't know our own
'Cause
address.
we're off the main street, so yeah, it's Boulevard.
So 7525 Northwest 4th Boulevard. Now, Northwest 4th Boulevard is our street, and we share that with a number of other buildings. So there's probably a 7527 or a 7523 on our side of the road, and on the other side of the road, there's probably a 7526 and a 7524.
Even odd.
And we're all on Northwest 4th Boulevard, right? So think of that as like the network. And then 7525, we're the only 7525 on Northwest 4th Boulevard,
Yes.
right? That's the host. But there could be a 7525 on Northwest 5th Boulevard or Northwest 6th Boulevard. That's a different street, right? Well, that's how networks are. At one point, this address will get divided, and part of it will be the network, and a bunch of computers will share that network, and then the other part will be the host ID. Well, in the early days, the classes defined that, and they defined it through a subnet mask, and it was actually written like this: 255.0.0.0, or for class B, it was 255.255.0.0, and for a class C, it was 255.255.255.0. These are 4 numbers, right? Just like our IP address is made up of 4 numbers. And where there's a 255, that would identify the network. And where there's a 0, that would identify the host. So if I was in a class A, then the 10 would be my network, and 0.11.49 would identify my laptop. But if I was in a class B, well, 10.0 would be my network, and 11.49 would be my laptop. And if I was in a class C, 10.0.11 would be the network, and 49 would be the laptop, right? So that class really makes a difference. But you probably noticed when I was in my IP ADDR output that my IP address was listed here as 10.0.11.49/16. It's not showing 255.255. Whatever. I don't see that. That /16 is actually counting up bits. It's saying there's 16 ones followed by 16 zeros because it's a 32-bit address. And that's actually telling me the class, right? If we were to convert these into binary, they would actually look a little bit different because, for example, 255.255.255.0 would be written as a /24, or 255.255.0 would be a /16, and then the class A here would actually be written as a /8. So those are kind of abbreviations for that network. So IP ADDR is actually telling me what my network is. It's just writing it in what's called subnet shorthand, right? So that's how our network addresses are built up, how they're kind of created. And we have these different classes that aren't really followed anymore. These were rules that were created way back in the 1980s that over time have been kind of broken and moved away from. And so you'll see networks that deviate from this wildly, and that's perfectly fine. It's not a bad thing. It's not like somebody's breaking the rules. The rules have gone away, right? But most people still follow the main boundaries. You'll still see /8, /16, /24, just like I've got here, but laid out with all sorts of different numbers. Now, which type of network we use generally depends on how many hosts we need, right? If the first 3 numbers are all tied up in my network ID, that only leaves 1 number to represent hosts. So that's going to be a pretty small network. But if only the first number is used for the network, then I've got these 3 remaining numbers that I can use for the host. That's going to be a pretty big network, right? And to give you an idea of the sizes on these, a Class A network can actually hold 16,777,214 hosts. Can all fit on that network. That's a lot of computers, more than what most people need. A /16 can hold 65,534 hosts, and A/24 can hold 254 hosts. See how they get smaller and smaller as they go, right? Well, if you're on a home network, odds are you're going to have less than 254 hosts. And so a Class C type network works out. And that's why you see so many homes set up with 192.168.0.1 slash 24 or 255.255.255.0. That's pretty common because of the size of that network. So that's how these addresses are kind of arranged, and your system is able to use that to learn about what other addresses are on the same network or addresses that are on a different network. In other words, we've got to pass through a router to get to them. So that's kind of why we have those addresses in place.
So, Don, how do we choose which addresses to use?
That's a good question because I'm throwing out some random numbers here, right? But in real life, it's actually not very random at all. You have private IPs that you can use freely, that you can pick amongst to your heart's content. Doesn't really matter which ones you use. But there's public IPs, the IPs that are used out on the internet, and those have to be globally unique. In other words, you're not allowed to use an IP somebody else is using. Well, if we expected the world to be nice about that and everybody just not duplicate, that would never happen. So there's an organization called the ARIN, and they're a numbers registry. They actually collect all the IP information and they assign out IPs to make sure there's no duplicates. So on the internet, you have to use registered IPs. On your own network, you can use private ones, fake ones. And let me bring up a diagram I got parked over here. Here we go. So on our LAN, oftentimes we will use fake IPs. Like here, they're showing 192.168.1.0/24 on the LAN. But on the internet, we need public registered IPs. So we may have a router that's doing network address translation that's hiding all of our fake IPs and translating our traffic into one shared public IP so we can go out to the internet. And on the internet, it'll just see that one address. When you connect to a cable modem or DSL or something of that nature, they're usually giving you one public IP. If you're on a Metro Ethernet network, then maybe you have public IPs on all the different systems, but usually it's not like that, right? So when we pick IP addresses to use in our own network, we need to keep them into a specific range. Let me go back to my little text file here. The IEEE is a standards organization, and they work closely with the ISO, another standards organization, and they create various standards. And there's one standard, which is RFC 1918, which sets aside 3 ranges of network addresses for us to use in our internal computers, right? So for our internal networks, the most popular one is an old Class C that was set aside. Actually, it's several Class Cs. 192.168.x.x/24, okay? And as far as Class Cs go, that would be 192.168.0 all the way through 192.168.255, or really 254.0, right? Would all be kind of set aside. So that's 255 Class C networks that are available for us to use privately in our network. We don't have to register those. You can just use them to your heart's content. On the Class B side, they did 172.16.whatever, all the way through 172.31.whatever, and those are all /16s. So if you want a Class B size network, 65,000 hosts, they actually set aside 15 of them or 16 of them that you can use, again, to your heart's content, and you can use them without registering. All right, and then on the Class A side, they set aside 10.whatever, which is A/8. So if you want to use a Class A, you certainly can. And then you can do things like what we're doing right here. If you looked at my IP, it starts with 10 dot, which would be that Class A that's set aside, but I'm using it as a /16. So here in the studios, we've taken that big Class A and divided it up, chopped it up into smaller networks to use it, so they're all under one umbrella, under one big network. And that's super convenient. Really does make life a lot easier for us. And that's how that's kind of arranged. So when you go to pick an IP addressing scheme to use for your local network, you're usually going to pick from those public addresses.
What about IPv6? I hear it's significantly different.
It is, yeah. You know, IPv4 it's a 32-bit address. And that means that there are roughly 4.3 billion addresses available in the entire IPv4 address pool. Now, when that was created back in the 1980s, the late 1970s, 4.3 billion was a lot of addresses. Back then, the world's population was like 4.3 billion, and most people didn't have computers. And so they figured this is way more addresses than we'll ever need. We're covered, right? But today, the Earth's population is over 7 billion. And a lot of people have computers. And beyond that, most people have a computer, a cell phone, some kind of streaming media box in their home. People have multiple devices. And so 4.3 billion addresses, not enough, running out. Okay. So instead, it has been it's been recognized that IPv4 is running out. So they created a new protocol called IPv6. And with IPv6, they moved from a 32-bit address to a 128-bit address. And that is a big, big address. I forget the name of the number. It's something like over one
Undecillion.
undecillion. Is that it?
Undecillion, yeah.
So over one. I'm glad you remembered. Over one undecillion addresses. I mean, it's big, right? So it's best not to even think of it in those terms because that number is meaningless to us, right? So let me put it in a different way. IPv4 has 4.3 billion addresses, right? The Earth's population is over 7 billion right now. With IPv6, we could give 4.3 billion addresses to each individual person on the planet and still have addresses left over.
I need that much. I really do.
It's big, right? So they said, we made the mistake before. We're not making it again. We want to have enough addresses. And so they created this new standard. It's intimidating because of that. IPv6 addresses are big, right? And let me just show you, when I pulled up my IP address earlier, I have INET right here. That's actually talking about IPv4. But right beneath that, I've got INET 6. There's an IPv6 address that I have in my system. And it does not read as easy as IPv4. My IPv4 address is 10.0.11.49. My IPv6 address is FE80::C3F7:23E6:E6CE:32EE. And that's even abbreviated. These double colons right here tell me there's some collapsed fields that were just all zeros, right? So an address there can actually be significantly longer. And I'm in a /64, so that is telling me right there that the first 64 bits of the network, the last 64 bits of the host. Either side has 64 bits. IPv4 was 32 bits for the whole darn thing, right? Network and host. So it is a big, big space. You are going to see IPv6 more and more coming down the line. That is not something that's going away. It's got new features in it that make it more powerful, and more networks are moving to that. If you haven't looked, the odds are you have an IPv6 already, either on your machine or on the router for your network that connects to the internet. But more and more systems are moving that way.
Don, we've been talking about IPs, so where does TCP come in?
All right, so back in the beginning of the show, I said we're going to talk about the TCP IP protocol stack.
Yes.
And so far, I've only talked about IP, right? So IP is the internet protocol, and it's responsible for addressing. That's what we've been talking about, right? So how do we know where we're going to go? But once we get where we're trying to go, we need to talk to software. And that's where TCP comes in. TCP is the transmission control protocol. And what TCP does is allow us to establish a session between us and the other computer that we're trying to talk to. It's very important. Let me bring up a different diagram, if I can try here. There we go. And what we're looking at here is the internet protocol, or the TCP IP protocol stack, right? It's made up of a number of different components. Down at the very bottom, you're seeing the hardware, what's called the media access layer. And this is where we have Ethernet and wireless, right? If you've got fiber optic or copper cabling plugged in, you're likely using 802.3 Ethernet. I have to say likely because there are a few other standards out there, but you're probably using 802.3 Ethernet. Or if you're using Wi-Fi, then you're using 802.11 wireless, and any of the variations that are in there, 802.11 A, B, C, G, AC, there's a bunch of them, and it goes on and on, right? So that's your network connectivity. Then you run IP on top of that, because that's the addressing, how you can find where's your traffic coming from, where's your traffic going to, how do you get routed there? That's what IP does. But on top of IP, there's actually a handful of other protocols, TCP and UDP. So TCP is Transmission Control Protocol, and it's responsible for making sure your data gets to where it's going, right? With TCP, it's a connection-oriented protocol. So when you send something to another server, the other server is expecting it. And when it gets it, it replies back to say, yes, I got it. So we know that it made it there, right? We have a guaranteed delivery. If it doesn't get to the other side, then the other side will send us a message and say, hey, something went wrong. I didn't get that. And we can retransmit and send it along, right? So like if I fire off an email to Zach and a day goes by and I don't hear anything from him, I might say, Zach, did you get my email? And he might say, no, I didn't get it. All right, well, you know what? Let me go back to my computer. I'll resend it.
Okay.
That's what TCP does, right? TCP just resends when necessary.
Okay.
Sometimes we don't need that though, right? Sometimes that can be a problem. Imagine you're doing a voice over IP call and maybe I'm calling Zach on the phone and he's on the other side of the world, right? You're on vacation in Fiji. And
Oh,
which
yeah, I
would
go
be
there
nice.
every week.
So that's a long way away, right? So likely we're going to have to use a satellite phone, and I'm going to say something. It's going to take time to get over there. And then if it doesn't get there, or even if it does get there, right? And then he sends a message back saying, yep, I got it. And then I start talking, like it creates a delay. And if something gets missed, I've got to retransmit it. Now the delay is even bigger. And the delay gets bigger and bigger and bigger with every missed packet. That becomes a real problem, all right? So there's times where it's better to say, you know what, I missed something, but let me just skip it and move on, right? Think about like streaming video with sports. You're watching a football game and the ball is going through the air and you drop a packet. Well, you don't want to go back and capture that. You just skip it. The ball moves forward a little bit more and then keeps going. You want to stay as close to real time as possible. Video streaming, voice streaming, that kind of stuff. You want to stay as close to real time as you can. So what UDP does, UDP is the user datagram protocol, and it's what's called a best effort algorithm or protocol. And what it does is it says, I'm going to make my best effort. I'm going to chuck the data in the right direction. But if it doesn't get there, oh, well, I'll just move on and that's it. And that's perfectly fine for things like streaming video and audio. Not fine for email. I tried to send it and then I gave up. I might as well use the postal service, right? You have better odds with the postal service than with UDP. But with UDP, it doesn't go back and do acknowledgments and verification. It doesn't have a session, right? It's not a true connection to the other side. It's just throwing the data along, and that's suitable in some areas. But TCP is really the one that does the work, and that's why they call it the TCP IP protocol stack and not the UDP IP protocol stack, because UDP is not that common. Now, on top of TCP, we then have all of our other protocols, things like HTTP for browsing the web, FTP, SMTP, all these other different things that we use to actually talk to software. But they wouldn't work if they didn't have TCP to build the session in the first place, then to start transmitting.
Well, Don, can we see all this happening in the background?
You can. Just about everything I've talked about this episode is like secret, hidden in the background, stuff that end users don't normally get exposed to. Yeah. I mean, you can kind of interpret it that way. This stuff just works, right? Now we sound like a Steve Jobs commercial.
I know we do.
But it does happen. You can see this stuff going on. Let me just show you an example. I need to pick somebody to talk to. All right, I'm going to pick something fun. So there is a site where they have created, they've recreated the entire Star Wars movie, the first Star Wars movie, in text animation. It's really, really neat.
What?
I know, it's cool. So let me just do a quick NS lookup. So there's a site. It's called towel.blinken, if I can spell it here, blinkenlights.nl. All right. So I'm looking up the address to this system, okay? So I know its IP right here, 94.142.241.111. Let me just copy that. So I've got it. Okay. Now, I can browse that server with a web browser, right? You go to www.facebook.com, right? So you're browsing the Facebook website. You don't need to know the IP. You don't need to know if it's TCP or UDP. You don't care about any of that stuff, right? You just know the name. And that's the experience that most people have. They just know the name and that's it. Well, in this case, I'm going to use Telnet to connect to that. And let me just paste that in. All right. And, I don't have Telnet installed, so let me just add that real quick. Otherwise, I'm not going to be able to Telnet. So once I've got that there, let me just Telnet in. All right. So here we go. We connect up, and I'm now in a Telnet session. And Telnet we don't use all that often, but I picked this one because it's going to hold a session open for a while. With web browsers, if I browse to Facebook, I load the page, and then my session stalls, right? And if it stays stalled long enough, the session closes. So it's kind of hard to see that going on in the background. It's very temporary, right? But here, it's going to play this whole movie. And so I'm connected, and it's going to start running through. And in the background, I've opened up a TCP session to their server, right? And I know it's super distracting. It's really awesome. But I've opened up a TCP session to their server. I'm sending data. They're acknowledging that they've received it from me.
Mhm.
They're sending me data. I'm acknowledging it to them. And if something gets missed, they retransmit it because everything is important in here, right?
Mhm.
Now, in the meantime, I can jump over here and let me get out of this, this little screen. All right. And that session's running in the background. I should be able to see that happening. And there's a utility called SS that we can use, which is a socket statistics utility.
Mhm.
When you build a session, they call that a socket. It's like opening up a socket to the other side. And software developers call it a socket. Network engineers call it a session. So it's different terminology, but it's the same thing. So I'm going to use SS, and I'm going to use -AN. Okay. A means I want to see all of my sessions, and N means don't do name lookups. Just show me the numbers. If it does name lookups, the command runs really slow. It takes a long time to do DNS lookups. So
Mhm.
I usually turn that off. And when I run that, I can see every session that I've got open on my system right now. You might have a ton of sessions, and I've actually got quite a few. So I'm going to rerun that, and I'm going to pipe that into the grep utility, and I'm going to look for the IP of that server that I'm connected to, right? There it is. Okay, I can see that I have a TCP session established from my IP right here to the server at the other end.
Mm.
And I can tell that it's telnet, okay? And I know that it's telnet because after the IP of the server, it says :23. And that :23, that tells me this is a telnet session. If I was browsing to a web page, it would be :80, right? If I, here, let's do this a little bit different. I'm going to go to grep for :80. Or can I just do :80? Oh, I don't have any web pages open. Here I am trying to find a web connection. So I don't have any open, but they would show as :80 or :443 if they were secured. You would see those sessions. You know, knowing those port numbers like that is really helpful to being able to identify the traffic in the background. The computer already knows the port number, so it doesn't make it user-friendly. But if you know them, you can easily spot that traffic and see what's going on in the background.
What port numbers should we be familiar with?
You know, it never hurts to be familiar with as many port numbers as possible. The more port numbers you know, the easier it is to recognize traffic. For the CompTIA exams, and not just Linux Plus, but really A Plus, Network Plus, and even Cisco, Microsoft. If you're doing any kind of certification exams, there's actually a laundry list of port numbers you should know. But in real life land, if you're going to become a network engineer, you're going to support Linux systems in the production environment. Knowing these port numbers can be really handy for testing firewall rules, for testing network connectivity, for monitoring traffic, and it's an important thing to do. So I have a little table, which I'll put in the show notes right here, with a bunch of common TCP UDP ports.
Okay.
And there's some protocols that use both TCP and UDP. Other protocols just use TCP. Some protocols just use UDP. That's good to know as well. I mentioned that port 23 was telnet, so I've got that one right here. Port 23, telnet. And it's using TCP. And we just saw all that in real life.
Mhm.
We know the protocol does that. But FTP, for example, uses 2 ports. When you connect, you're connecting on port 20 or 21. Shoot, I'm mixing them up. I think you connect on 20. And then once you connect and you start to send transfer commands, you transfer files on the other port. So it actually uses 2 different ports, one for commands and one for transferring data. SSH uses port 22. And all of those are TCP. In your mind, you can think, all right, would it hurt if I missed one of those packets, right? And in the case of a file transfer, absolutely, your file would be corrupt. It's got to use TCP. But there's other things like DNS. DNS can actually run on TCP or UDP. You can do either one. But with DNS, if you do a name lookup and it fails to get back to you, it's not a big deal because your lookup will just time out and you'll do the lookup again. DNS already has retransmit built into it, so we don't need TCP for that.
Mm.
It can use UDP and it's a little bit faster. So some protocols kind of speed up by doing that. Other protocols in the list, like Network Time Protocol, NTP, same thing, runs over port 123, so that one's easy to remember,
Mhm.
and it uses UDP because again, if you didn't get the time on the first try, retransmitting an old time is worse than just re-requesting the new time. So when you work with a time server, you'll always use UDP. You've got IMAP for email. You don't want to lose email. It has to use TCP, and it's on port 143. So I won't bore you by reading off all of these port numbers, but these are the pretty common ones. At a minimum, you need to know 22 for SSH, 23 for Telnet, 80 for HTTP, 443 for HTTPS, and 25 for SMTP. Those are really the biggest ones, but I would encourage you to memorize the whole table. It's a handy thing to have.
Awesome episode as usual, Don. Thank you very much. Understanding TCP IP. And before we leave, I know there's something else you'd like to say.
Yeah, let's jump back to my computer for a second, because we just saw the text part of Star Wars. Now we get
I
the
was
cool
just going to say, I want to
animation
see
right
more
here.
of it.
And so there's Luke scanning, trying to find R2-D2 in the desert. So it's pretty awesome. There's fun stuff on the internet if you find it.
That's awesome stuff. It really is. And there's a lot of great material, learning material, and fun, and more shenanigans than we can possibly place in one episode. So you have to see every single episode of CompTIA Linux Plus. Don's done a great job putting this series together for you, and it will help you when that exam comes rolling along. And don't forget about the supplementary information that's available in our course library that will help you do one thing: go even further. Check it out. And tell everybody you know about IT Pro TV. IT Pro TV is binge-worthy. Thanks for watching. I'm Zach Memis.
And I'm Don Pizzette.
We will see you again soon.
Thank you for watching IT Pro TV.